Okay, today's lecture is Professor In-Hoo Jun from the Seoul National University. Let me introduce him first before the lecture. His major research area is thermodynamic database development for pyrometrology process and alloy design, and also as the development of process simulation model for steel making. But I believe Professor Jun is doing both calculation and experiment. So it's beyond my area, and I really recommend you to listen to this nice lecture. And briefly, I'm going to introduce his history. He graduated from Pohang University of Science and Technology, POSTECH. Everybody knows this. And in 1997, then took master in 1999. And then he went to Canada, the École Polytechnique Montreal, and then he took PhD there. And after that, he spent many years in Canada, about 20 years?
Yeah, almost 20 years.
20 years. And he was assistant professor and associate professor from 2007 to 2017. Then he came back to Korea and as in Seoul National University. Then he promoted to professor this year. So now he's a very young but very active, one of the most active professor in the world in our area. So please do a lecture. Thank you very much for your contribution.
Thank you very much, Professor Morita. And I hope everyone can hear me well. Is it okay?
Yes, Professor.
Okay, good. So first of all, thank you very much for inviting me to give this lecture at the University of Tokyo. I've been visit actually University of Tokyo several times, both in the Honggu campus and also Kashiwa campus. Am I right? It's in the outside of the Tokyo, and also the Tokyo Institute of Industrial Research Science and Technology too. So unfortunately, in this day, we cannot actually visit each other. So, but I'm still actually, very happy actually to give this lecture through the online, actually the meeting like this. Okay, so today's my talk is the title of my talk is From Thermodynamics to the Smart Steelmaking Factory. So the talk, within this talk, I'll introduce a little bit about, I'll introduce you the engineering thermodynamics, what we have learned in the undergraduate level, and then going to develop slowly toward the smart factory, which I'm doing in this day. So this is the content of the talk today. So first, I'll probably spend about the 10 or 20 slides about showing you the review of our engineering thermodynamics, and then show you a little bit about how to develop so-called CalPad thermodynamic database. And then I'll show you how to apply this kind of database for some thermodynamic actually the problem in the industry. And also eventually I want to combine this thermodynamic and kinetics together to go into the so-called smart factory system in steelmaking. So let's start with a review of the thermodynamic, engineering thermodynamics. I think all of you probably learn thermodynamics. If you are in the engineering school, either you are in the material engineering department, material science and engineering department, or even in chemical engineering, even in the mechanical engineering, you always learn thermodynamics. And a lot of people believe that, feeling that thermodynamics is very difficult subject. And when I was actually the student, undergraduate student, I actually felt the same way. And one of the reason why we believe thermodynamics was very difficult, thermodynamics is very difficult, is most of the time we are learning thermodynamics through the equation itself. And we don't see why we are learning actually thermodynamics, because we didn't see that many examples about how to applying this kind of thermodynamics for the real process question, So that's why we always see that thermodynamics is very difficult, actually, the knowledge. And so when I actually teach the thermodynamics in the university here, in Seoul National University, and also in the McGill University for 10 years, I try to give actually give the lecture about thermodynamics by using a lot of the examples, and not like a theoretical examples, more like a practical example, which is really which relate to some industrial problem. And through that, I found out that students can actually enjoy the thermodynamics, and they really learn why thermodynamics is very important. So I'll try to actually remind you today why, the basic equation about thermodynamics and how to utilize this kind of concept in the industrial problem. Okay, so we learn all 3 laws of the thermodynamics, okay? And first law, second law, and the third law of thermodynamics, of course. So we have lots of students here. So let me ask you, is it possible to actually turn on your microphone? So Hibi, Koki Hibi. Can you hear me?
Yes, I can hear you.
Yeah. What is the first law of the thermodynamics?
So how can I say it in English?
Oh, you can say in Japanese too.
まあ、仕事ですよね。
Unfortunately, I don't understand Japanese. Is there anyone who can translate for me? So first, yeah.
Yeah.
Go ahead.
It's just work and energy, and I forgot the word. Sorry.
No problem. So typically we say that, you probably remember that du equal to dq minus dw. Yeah. That's the typical equation we are learning for the first law of thermodynamics. But the concept of the first law of thermodynamics is energy conservation. So for the given system, you actually exchange with the surrounding, the energy like heat and work can be exchangeable. That's actually the first law of thermodynamics. So the energy of universe is constant. That's the first law of thermodynamics. Okay. So then how about second law of thermodynamics? So we have some Chinese student here too. Li Wang. Li Wang. Can you hear me? Oh, I don't have any response. So how about the Byung-tae Che? He's actually my student. So forget about it. Chao Yongpeng.
Yeah, professor.
Yeah. So what's the second law of thermodynamics?
I think sorry, I just Googled that. Can I just do you need me to repeat the definition?
Yeah.
Okay. So, irreversibility of natural processes, and it's the Q equals to T multiply derivative of S. Yeah.
So I don't know.
Sorry.
So second law of thermodynamics is this one. So second law of thermodynamics is about the entropy. So entropy of universe is increasing for any kind of the natural process or any kind of spontaneous process. So if you just leave the natural in general, second law of thermodynamics means when you just leave something as it is, by nature, it makes more disorderly. That's the second law of thermodynamics. Okay. So then let's go to the third law of the thermodynamics. So who I can ask? Yoshio Aoki.
Yes.
What's the third law of thermodynamics?
And the third law of thermodynamics, it means that at 0 Kelvin,
Mhm.
なんだろうな、the entropy of the perfect crystal is the same.
Same or
I think.
zero? Zero. Yeah, that's correct. So entropy of the perfect crystal or stoichiometric crystalline material at 0 degree Kelvin is zero. That's the third law of thermodynamics. So you see, I mean, you learn the thermodynamics, even you don't remember first, second, and third law of thermodynamics. Because, in fact, you don't need any of this law to apply the thermodynamics. Okay, so I just want to actually refresh you a little bit. And I mean, I hope everyone can actually more focus on this lecture. That's why I actually bring up these three laws of thermodynamics. But most important thing, what we're actually learning in thermodynamics is typically Gibbs energy, especially when you're in the material engineering, actually the department, we learn the thermodynamics through the Gibbs energy. Gibbs energy equal to enthalpy minus T entropy. And now let's look at actually how we develop all the thermodynamic equation. So for the pure element or pure compound like aluminum, pure aluminum, solid, liquid gas, or oxygen like a gas, Al2O3 like solid or liquid phase, and their Gibbs energy can be written in this way: G equal to H minus Ts. Especially here, I put the circle here, and we call this one G naught, or equal to H naught minus Ts naught. And each of these function is the function of temperature, and the H here is expressed in this way. H at given temperature is H standard enthalpy of formation at 298 Kelvin plus integral heat capacity dt from 298 Kelvin to the certain temperature. Okay, and entropy of the given stoichiometric material is also expressed similarly like this. Okay, so in order to define the Gibbs energy of the stoichiometric material, okay, pure material when I say, and compared to the actual solution phase, if you actually have the pure stoichiometric phase, the Gibbs energy of each of this one can be defined by H298, S298, and Cp. So if you know all these three functions, we can define the Gibbs energy of each species. Okay. Now, when you actually combine this kind of the pure species, then we can make already chemical reaction. So let's look at this kind of chemical reaction. N moles of A plus M moles of B become ANBM phase. Okay. So for example, iron plus carbon become iron carbide. Okay. So all the solid phase. And there's no, for example, if it's all pure component, then we can define the Gibbs energy of reaction, because this is chemical reaction, as a product Gibbs energy minus reactant Gibbs energy. Product is the pure ABN, so not means pure material. It's not solution material. So G of ANBM minus M moles of GA plus M moles of GB. And Gibbs energy is expressed by H minus Ts, so we can recombining them as this one as a delta G of reaction for all the pure species equal to H minus Ts. And typically in the thermodynamic book, when you look at the actual table, there's they actually list of chemical reaction like this, and then provide you H and S value as A plus BT. And this is actually very useful information already to understand the chemical reaction. And now when you're actually combining this one with the gas phase, we can develop equation like this. A reacting with oxygen become A oxide, for example. And then if you write the actual chemical reaction again, Gibbs energy, delta G of reaction equal to product Gibbs energy minus reactant Gibbs energy. And however, this reactant, among the reactant, if the oxygen here, which is gas phase, if the gas phase have, gas is not pure oxygen gas phase. If it is, for example, oxygen with a nitrogen gas, then we have the mixture, gas solution phase already. So when you actually have this kind of solution phase, we have to include some additional correction energy like this. So Gibbs energy of the oxygen become pure Gibbs energy of oxygen at 1 atm, pure oxygen condition, plus we have partial pressure correction here. So this is because of the solution, yes. Okay. Then if you combining them again, then you can get pure Gibbs energy reaction minus mRT ln PO2. And if you assume this left side and right side of the chemical reaction is in equilibrium condition, then we can assume that this Gibbs energy difference between reactant and product is 0. Then we can derive the famous equation, delta G of reactant, G naught of reaction equal to minus RT ln 1 of the partial pressure. And this partial pressure is the PO2, which require to make your A phase and A oxide phase can exist together. Okay. So for example, if you have an iron and iron oxide is existing together in your system, then you have to know what would be in order to make iron and iron oxide equilibrium together in your given system, you have to define proper partial pressure of oxygen. Okay. And that partial pressure of oxygen can be calculated by using this kind of the equation. If you have a higher partial pressure oxygen than this equilibrium partial pressure of oxygen, then you're going to make oxide. And if you have less partial pressure of oxygen, then you're going to make metals. Okay. So equilibrium condition is very important to determine. And now if you actually go to the more complex system involving more than 2 gas species, so like A plus B gas becomes C plus D gas, then at equilibrium condition, you can also get this kind of relationship. Here, this term here, we call it as equilibrium constant to make actually this reactant and the product can exist together. And so a lot of students actually remember only this equation, delta G of reaction equal to minus RT ln K equilibrium, okay? And this is first of the problem. This is the first problem we learn thermodynamics. Because in the most of the case, we have given equation, and then we try to solve that actual problem based on the chemical equation. Then for that, we need only this kind of equation. But however, if you go to the real problem, we don't know, first of all, what kind of chemical reaction we have to consider. So it's much complex. Okay. Nevertheless, I mean, if you actually consider this kind of chemical reaction, we can, I mean, one of the actually most famous graph in the thermodynamics is so-called this kind of Ellingham diagram. So Ellingham diagram is the collection of all the Gibbs energy of the reaction, pure to pure reaction with the temperature, especially including the oxygen as a reactant. So for example, here you can see that 2 moles of iron plus 1 mole of oxygen become 2 moles of FeO. And this line showing you the Gibbs energy of reaction, delta G of reaction in y-axis, changing with the temperature, okay? So if you actually look at this kind of diagram, this kind of diagram is very useful to determine what kind of oxide is more stable than the other oxide, okay? So one of the reaction actually we can consider is this kind of thing. So we have, let's assume we have 2 moles of oxygen, 2 moles of iron reacting oxygen become iron oxide. So this is this graph. And then we have 2 moles of carbon reacting with oxygen become 2 moles of CO gas. That's actually corresponding to this one. So if you're combining these two equations together, we can get this one. Iron oxide plus carbon become iron plus CO gas. Is this chemical reaction can go to the forward reaction or not? That's determined by the Gibbs energy of reaction. So if the Gibbs energy of reaction for this one is negative, then we can actually get forward reaction. So it means we can react iron with carbon to produce iron oxide, iron metal, iron oxide with carbon to produce iron metal. So if you look at the graph here, so this is CO and this is FeO. So if the temperature is above this temperature, so all this area here, you can have a negative delta G naught of reaction of this chemical reaction. So it means under that condition, if you consider everything is the pure material, including the CO as 1 atm partial pressure, then you can make this reaction going to the forward. Okay, so that's the actual value of the Ellingham diagram. And so, for example, now let's look at the other one, iron oxide plus carbon, calcium. So calcium is here. So calcium plus calcium oxide. So if you react the iron oxide with the calcium, and you can produce calcium oxide and then produce iron metal. So from this energy difference, we can say that way. Okay, so it looks very easy. Now let me ask you one quiz here. So according to the phase diagram, here we have calcium oxide line here, and we have the magnesium oxide line is here. Can you see these two lines? And then my question is like this. If we put the calcium oxide into the liquid magnesium at 700 degrees Celsius, so here 700 degrees Celsius at this point, can calcium oxide be reduced to make a calcium metal and magnesium become magnesium oxide or not? This is my question. So let me ask you this question to the Masaya Higuchi. Masaya Higuchi. Is he not there? Then Ying Li. Ying Li. Okay, so you don't have actually the voice. So what's the answer? Higuchi? Yes or no? No. Very good. So any other student who say no, can you raise your hand? Is there any student who say yes? So most of students say no. I see actually some students say yes. Akinori Nakayama. Akinori Nakayama. Why do you think this is yes? Akinori Nakayama. So a lot of students say it's no, but in real actually answer is yes. CaO can be reduced to the metal. So you say no, okay. So you actually, the real answer is yes. So if you look at actually this equation here, I mean this chemical reaction, according to this Ellingham diagram, delta G naught of reaction is actually positive. So we think this chemical reaction cannot happen. We cannot go to the forward reaction. It should be backward reaction. But in reality, this is delta G naught of reaction, okay? However, if you want to know whether chemical reaction can happen or not, you have to consider delta G of reaction, not delta G naught of reaction, delta G of reaction, okay? So if the delta G of reaction is less than 0, then it can make a forward reaction. If it's higher than 0, it can make a backward reaction. If it is 0, that's the equilibrium state. So in the previous actual slide, I show you that delta G of reaction equal to 0 at the equilibrium condition. Yeah. So that's the assumption. And delta G of reaction, if you look at it here, we're containing delta G naught of reaction, pure Gibbs energy, assuming everything is pure, plus some additional correction term, and containing, in this case, activity, so-called activity. I think all of you learned activity before. And so this activity is depending on your system. It's changed by the interaction with the surrounding actually species, okay? Especially when you make a solution phase. So we cannot have the only one solution. If this is always higher than 0, people cannot do anything. We cannot produce calcium, yeah? But by changing the some environment, by putting our idea, we can change this problem, okay? We can actually change this reaction as a reverse reaction, okay? So in reality, in this case, and if you look at real actual answer, we can make calcium can dissolve into the liquid magnesium up to 10%. Of course, we cannot make a pure calcium, but we can make a calcium, magnesium, liquid solution, okay? So then, I mean, this activity is very important actually to understand. So let's look at the activity. So in the gas phase, we learned that gas Gibbs energy in solution is the pure Gibbs energy of gas at 1 atm plus RT ln partial pressure. So this is the correction term for the gas solution phase. Okay. In case of the solid or liquid solution, the Gibbs energy of species in the solution is the pure Gibbs energy plus RT ln activity. This pure Gibbs energy is, we can get it from the thermodynamic table. And this activity is depending on the species in your solution. Okay, so this is the correction term coming from your surrounding species. Okay, and this kind of correction term, as I say, it's changing depending on your surrounding material. So, for example, you can make ideal solution, you can make a negative deviation solution or positive deviation solution from the ideal solution, depending on what kind of species you are mixing together in the given solution phase. So for example, if the calcium and magnesium like each other, then the activity coefficient is less than 1. So it's more stable because it like each other. But if calcium and magnesium don't like each other, if they hate each other, then it have the repulsive force, then the activity is higher than 1. Activity coefficient is higher than 1. So by changing your surrounding species, you can actively control the activity. And this is actually where we have to put our idea to design the system. So the activity is very important. So if you consider now those activity for this kind of general system, A plus B becomes C plus D, and the reaction Gibbs energy of this one is product Gibbs energy minus reactant Gibbs energy, and then you can summarize that as a delta G not of reaction between the pure species plus correction term like this. And equilibrium condition, at equilibrium, this delta G of reaction equal to 0, then you can recombine them, and then you can express in this way. Delta G naught equal to minus RT ln activity. In this activity, we have activity coefficient and the mole fraction. So if you know if you assume the equilibrium condition, we can calculate what would be the composition of each phase, for example, in the liquid phase and in the gas phase. Okay. So I'll show you later, but the thermodynamic database, the CalPad type thermodynamic database, containing the equation for the partial Gibbs energy of the species in the solution, and that means we know activity of species at the given composition and given temperature for solution phase. So we can calculate this kind of equilibrium condition very easily. Okay, so let me go back to this question again. So as I showed you before, we have magnesium oxide and calcium can react together because magnesium oxide is less stable than the calcium oxide. If it's the pure, everything is pure material, then this reactant have the higher Gibbs energy than the product. So we'll have the forward reaction naturally, okay? But if I actually make this calcium and the magnesium as a solution phase, as a liquid solution, for example, then the Gibbs energy of the solution can be changed from the pure plus additional activity term here. If the activity is less than 1, then this becomes minus value. So partial Gibbs energy can decrease. So it means this Gibbs energy can decrease further. So you can actually reduce your reactant Gibbs energy. Okay, so it's still forward reaction, but it's much less actually the Gibbs energy. And now if you reduce further and further, then you can eventually go to the equilibrium state. So both reactant Gibbs energy and product Gibbs energy is same. And you can even make the other way around if you change this one properly, okay? So my message here is, if you control the environment, if you control the surrounding species, then we can produce something which is unfavorable in nature, okay? So we can change what God make for us, okay? And you need your idea now. We have to add idea. And the key point is this activity. Okay, so I think all of you probably also seen this kind of equation. So when you have the AB solution, for example, solid or liquid solution, the Gibbs energy solution is mole fraction of A times Gibbs energy of the A in the solution, and mole fraction of B times Gibbs energy of B in the solution. We call this one as a partial Gibbs energy, and partial Gibbs energy was expressed in this way. So we can rewrite equation of the solution in this way, okay? Here, this pure Gibbs energy, we can take it from the thermodynamic table, and activity is something we have to determine by experiment, or if you have the good thermodynamic database, we can calculate this one directly. In the ideal solution, we assume that this activity coefficient equal to 1, so activity equal to activity coefficient times mole fraction, then we can make a very simple ideal solution model like this. And if we consider regular solution, so when the RT ln activity, you have a special relationship like this, we call this one as a regular solution, then we can express this Gibbs energy of solution in this way. But to say frankly, I do a lot of the thermodynamic assessment to find out that this Gibbs energy for the solution phase. Among all the solution, all the binary system we have to deal with, only about very, very few % of the solution is close to the ideal solution or regular solution. And the rest of them is much complex. That's very natural because the interaction between the species can be changed depending on the composition and temperature, okay? So in general, this activity coefficient is function of both composition and temperature, and then we can express Gibbs energy, much more complex system like this. And this g-axis here is can have actually the parameter, which is function of the temperature and the composition like this. So if we know this omega parameter as a function of the temperature and the composition like this, we can calculate the activity coefficient. If you know the activity coefficient, we can calculate what is the equilibrium state. That's what we want to know. For example, Professor Morita in your department spent probably almost his entire life to find out that this activity coefficient in the different kinds of the metallic system and the oxide system, okay? Because this is very important value. So over the last 60 years, or almost 70 years, in the thermochemistry, area, people spent most of their energy to find out that this activity coefficient at the given system, at the given temperature, okay? And now, we can also connect this kind of Gibbs energy with the phase diagram. So phase diagram is the graphical representation of the Gibbs energy of the system, okay? So for example, this is the AB binary phase diagram. We have liquid phase, we have alpha solid solution, beta solid solution here. And if you actually look at the Gibbs energy curve at this T2 temperature, we can draw the Gibbs energy in this way. So we have beta solid solution Gibbs energy, we have alpha solid solution Gibbs energy, we have liquid Gibbs energy. And this phase diagram show you equilibrium phase at the given composition at T2 temperature. So for example, at this composition here, we have liquid phase, okay? So at this composition here, liquid have the lowest Gibbs energy among the all three solution phase. That's why liquid is the most stable state, okay? That show you that liquid is actually, and then in order to actually consider the possible two-phase, actually the combination, we can consider also so-called Gibbs tangent line, and then find out either single phase or two-phase have the minimum actually Gibbs energy of the phase, considering both single phase and the two-phase. Then in this area, alpha have the lowest Gibbs energy. Here in this area, liquid plus alpha, for liquid this one and alpha this one, have lowest energy, and then liquid is lowest energy here, and etc. So if you actually put this boundary in the phase diagram, you can create the phase diagram. Alpha and alpha plus liquid phase area, liquid plus beta, beta single phase area, okay? So phase diagram is highly related to the Gibbs energy. So if we find out all the Gibbs energy of the system with the temperature and composition, we can back calculate our phase diagram. And the other way around, so if you know the phase diagram, we can also more or less estimate what would be the Gibbs energy of each phase. So this is what have a one-to-one relationship. So now let me actually show you what's the CalPad, okay? So we learn actually the basic thermodynamics, and if you actually understand this basic thermodynamics, you can understand CalPad. So CalPad is so-called, CalPad is the acronym of the calculation of the phase diagram, okay? And CalPad actually society was started from 1973, but from already mid 1960, there's a couple of the research group in the world start to thinking, can we calculate phase diagram from the Gibbs energy function? Okay. At that time, the computer was not very well developed, but people using the very basic calculator to create phase diagram from the Gibbs energy function. Okay. So let me show you what is actually really CalPad method and how we developed the thermodynamic database. So as I mentioned, from the 1960, there was already some people start to actually doing the phase diagram calculation from the Gibbs energy. And already in the middle of the 1970, there was the commercial software was start to develop to calculate phase diagram and also do the very complex thermodynamic calculation. Okay, and FactSage and the ThermoCalc, these two is the most famous commercial software which is used in the metallurgical industry, and this is the longest, also had the longest history from the 1970. And then 80 and 90, there's the new actual software have been developed. So I'm actually personally working for the FactSage. I'm the one of the core developer of the FactSage software. So in the FactSage, we have the many thermodynamic database. So for example, here, PACT PS database, FT oxide database, and all this one is having different kinds of the application area. So how we develop the thermodynamic database, we actually collecting all the phase diagram information. As I mentioned, phase diagram information is like a Gibbs energy information. And then we collect all the thermodynamic data, like activity data, enthalpy data, heat capacity data, and etc. Okay, and by evaluating all these kinds of literature data, we try to find out Gibbs energy function for each binary system, ternary system, and the high order system. Okay, and then once we actually have those kinds of the database, we can enter to this kind of software. And then by using so-called Gibbs energy minimization routine, we can do the very complex thermodynamic calculation and also phase diagram calculation. So the equation is very simple. So for example, pure compound, this is exactly the same equation I show you in the beginning of this course. Okay, so we have Gibbs energy equal to H minus TS, and H is H298 integral CP, and S is S298 plus CP over the TDT. So in our database, we containing this H value, S value, and heat capacity for all the species. So for example, in the FactSage database, we have about 5,000 Gibbs energy function for the pure 5,000 the Gibbs energy function for the 5,000 species. Okay, and then if you combining pure components together, you can make a solution phase. For example, if you're considering the random mixing model, so it means ideal solution model plus some excess parameter, then for example, we have the AB solution, make liquid solution, then Gibbs energy of liquid can be expressed in this way. Mole fraction times pure Gibbs energy of A, mole fraction of the B times pure mole fraction of B, pure Gibbs energy of B, plus ideal entropy term and excess parameter. This excess parameter containing model parameter like QAB, and which is function of the temperature, and then this part considering the function of composition. So excess parameter can be function of temperature and the composition. So this is very simple thermodynamic model we can use, but in the most of the case, we are using more complex thermodynamic model, which is based on the structure, because structure is very important part when we developed solution model, and because entropy is very important to consider in the solution model. So entropy is depending on the structure of solution. So this kind of ideal entropy is not actually very well, not actually very applicable for the complex solution phase, solid solution and liquid solution. So we have different kinds of solution model reflecting those kinds of complex structure. Okay. So let me go back to this diagram again. So I show you already relationship between phase diagram and Gibbs energy diagram. Let me rephrase a little bit. So let's assume at this temperature, for example, and we have A in the solid state, B in the solid state, there's the liquid solution phase in this diagram. So in order to actually develop this kind of database, we need first Gibbs energy of the B solid phase here. which is function of H minus Ts. Okay, let's assume we have it. And then we can also define Gibbs energy of the B in the liquid phase, pure B, and pure A solid, pure A liquid. And then we have liquid is in solution. So liquid have some kind of the Gibbs energy function. And depending on your thermodynamic model, you can have different shape already. And then the shape here is also highly depending on the interaction between A and the B species in the liquid solution. If A, B like each other, if we have very negative interaction, then we can have much deeper liquid solution like this, okay? And so by using this phase diagram, so for example, at this point, we have liquid plus B phase existing together. So if you draw the Gibbs tangent, the tangent line in this Gibbs energy diagram, so this point here, which is the connecting point to the liquid phase, is the composition of the B at this composition. So the phase diagram can constrain the Gibbs energy already for the liquid phase. And then we can have at this point, for example, for the pure liquid, we can measure the activity of the A and the B, for example. Then according to the Gibbs energy diagram here, we can make a tangent line at this point. Then the point which is intersect to the pure B side, this Gibbs energy is the partial Gibbs energy of B at this composition, and that is connecting with the activity of the B. So by knowing the activity, we can also define how the shape of this Gibbs energy should be, okay? So in this way, we can collect all the thermodynamic data and phase diagram data, and we can evaluate them together to define this kind of Gibbs energy. So thermodynamic modeling is basically defined all the thermodynamic data by using the existing experimental data on phase diagram and also thermodynamic property. So this slide shows you one of the examples for the this is silicon tin, magnesium silicon tin ternary system. So this is ternary phase diagram. So how to construct this ternary phase diagram from the binary, and that's what I want to show you here. So this is the binary system, magnesium silicon binary system phase diagram, okay? So x-axis is mole fraction of silicon, y-axis is temperature, and we collect all the experimental data for the phase diagram. So for example, when we do the modeling, we are collecting the data even from the 19th or 18th or 19th century, so 18 something. So in this case, the first experimental data is coming from the 1909. And you see, it's a general shape of phase diagram was already revealed at that time, 1909. And then we collect all the other data too. So earlier data doesn't mean that this is have the more error. Sometimes earlier data is more accurate. Okay, so we collect all of them and see whether there's discrepancy or not. And then we're collecting also some other data. So for example, this liquid line is connecting with activity, as I showed you before. So here, for example, we have two sets of the activity data, but this set of the activity data is more well matching with this liquid data, because at this point here, at the given liquid point, your activity of the silicon in solid state in the liquid should be 1, because it's equivalent with the solid silicon. So activity is relating with your phase diagram. So by comparing these two data, we can already find out one of the data set is not actually consistent with the phase diagram. And then we also collect the data for the Mg2Si. Believe it or not, the Gibbs energy of Mg2Si was not available before I actually evaluate this system about 20 years ago. Okay, so here we have the heat capacity data, 3 sets of heat capacity data. One of them is different from the other 2. And then here we have Gibbs energy data. We have the enthalpy data. You see, enthalpy have the huge actually scatter, and you cannot have enthalpy data like this way. So some of this data is wrong. Okay, compared to the heat capacity and enthalpy, we can see that this enthalpy data and this enthalpy data, this heat capacity data is consistent with each other. If you know the Gibbs energy equal to H minus Ts, by knowing the H and the S and the heat capacity, we can get the Gibbs energy. So we can connecting all these 3 together as one function. And then this liquid shape here around this Mg2Si is highly depending on the Gibbs energy of liquid phase, because it's solid is fixed. And Gibbs energy of liquid, among the actually that Gibbs energy of liquid, the enthalpy especially changing the shape of these liquids very quickly. So here we have the enthalpy of the mixing data for the liquid phase, MgSI at the 1350 Kelvin. There's two sets of data. And if you take this data set, you cannot reproduce this liquid line. So this lower actual enthalpy data is more consistent with the phase diagram data. And also we have the two sets of partial pressure, partial enthalpy data, and this is way higher than the other actual data. And the other data is more consistent with this data set as well. So we're collecting all the data. We are not simply fitting the data, we evaluating them by using the Gibbs energy, and find out what's the most reliable data set. That's the thermodynamic modeling. At the end of this process, we can get this kind of data set. We have the Gibbs energy of the Mg2Si, enthalpy, entropy, and heat capacity. And then we have the liquid Gibbs energy, liquid solution Gibbs energy as a parameter like this. So we can enter this one into our database and back calculate all these kinds of function and phase diagram again. And this is another example, magnesium tin binary system. So here we have alpha solid solution, liquid solution plus Mg2Si 3-phase. And again, by using similar approach, we checked enthalpy of mixing for liquid phase and enthalpy change of Mg2SN solid phase, and activity data in the liquid phase, and also melting enthalpy of the Mg2SN from solid to the liquid state. So by reproducing all this data, in order to reproduce all this data with the phase diagram, we can find one set of the Gibbs energy for the liquid solution and Mg2SN and alpha solid solution. And then we can enter that into our database again. And then when you finish all the three binary system, we can compile them together to make a prediction for the ternary system. And also, this actually the step is very important. So there's the different kinds of interpolation technique of the Gibbs energy from the binary Gibbs energy. And so if you are using proper interpolation technique, you can make more accurate prediction to the ternary system. And this is the predictive, this is prediction from the binary to the ternary system. And original prediction was a little bit off. So we add a little bit of 1 or 2 excess parameter in the liquid phase to reproduce all the phase diagram more accurately. Okay. Then once you have this one, you can use this one, this thermodynamic database to calculate the phase diagram or to calculate enthalpy change from liquid to the solid or whatever you like. You can calculate activity at the given system too. Okay. So this is the one of the example for the how to develop CalPad type of thermodynamic database. So some people say that CalPad thermodynamic database development is curve fitting, but I have objection about that because you have to know all the experimental technique and you have to know how to evaluate the error in their experiment. And some of them, I never say that people make a mistake in the experiment. Typically, most of the time, we assume something, but that assumption may not working in the given experiment. So experiment was done correctly. However, people can interpret that result in the wrong way by using wrong assumption. Okay. So in our actually the lab, we try to look at the original experimental setup and try to think about any possible mistake in the assumption in the experiment, and then try to explain why the thermodynamic data is different from one data set to the other data set. In this way, we can evaluate the data correctly and we can provide more accurate data through this kind of evaluation and assessment. Okay, and once we have that good assessment, we can have resultant thermodynamic database. And we can store this one step by step, and then we can make a bigger and bigger database. So if you have the thermodynamic database, what we can do? Okay, so this is the LM diagram I showed you before. LM diagram is very nice diagram, but in all this Gibbs energy here, delta G naught here is the pure Gibbs energy between the pure species. But as I showed you before already, when you have the chemical reaction like this at equilibrium state, you have to consider this activity. Okay, if this is not the pure material anymore, then you have to know what's the activity coefficient and activity. And by knowing this one, you can calculate very complex chemical equilibrium. So in the thermodynamic database, we can provide information about activity for the given species in the solution phase. So we can calculate like this. So for example, if you have 40 grams of CaO, 30 grams of SiO2, 10 grams of the Al2O3, and 20 grams of the MgO, and 5 grams of Cl2O3 at 1600 degrees Celsius, I think nobody can answer what will happen in this 5-component system. But if you have the good thermodynamic database, then you can calculate what kind of equilibrium phase can be formed. So in this case, 93.3 grams of the liquid phase with the decomposition, about 6 grams of the spinel solution phase with the decomposition, and then about 6 grams of the monoxide, which is MgO rich phase in this composition. So, and whether this is correct or not, a lot of people prove that thermodynamic calculation is very reliable already. So you can believe that this is actually provide you very good answer already. Okay, so in the thermodynamic calculation, as I mentioned, if you're in the text in the thermodynamic class, we always know what kind of thermodynamic equation we have to use for the thermodynamic calculation. So for example, we have this kind of the chemical reaction we want to solve. Then by assuming delta G naught of reaction equal to 0, then we can calculate equilibrium constant here. Okay, and by using equilibrium constant and activity coefficient, we can find out composition of each phase. But in real actually the problem, you don't know even what kind of chemical reaction we have to consider. So for example, when you have m moles of A, n moles of B as input at the given temperature and given pressure, there's so many possible phase combination. So you cannot make actual chemical reaction. So you have one chemical reaction, one chemical reaction, one chemical reaction, one chemical reaction like this. And if you have the 5-component system, there's thousands of different possible chemical reactions you have to consider. We cannot solve this one by one by ourselves. But in this kind of thermodynamic package, we are using so-called Gibbs energy minimization routine, and which means any product which have the minimum Gibbs energy have the most stable state. That makes sense. That's a thermodynamic. Okay. So by using those kinds of minimum Gibbs energy minimization routine, we can calculate very complex thermodynamic equilibrium by using the thermodynamic database. And also, if you have this kind of thermodynamic database, we can do also temperature calculation very well. So heat balance calculation very well. So for example, let's look at this one. We have liquid steel at 1600 degrees Celsius and reacting with this ferromanganese at 25 degrees Celsius. So I'm adding this one into the liquid steel. And if we assume the adiabatic condition, so delta H equal to 0, heat loss equal to 0, what kind of phase will form with addition of X, with increasing of X, and what will be the final temperature? This is very complex actually question. If you ask this question to your student, or if I ask this one to the older student here, you have to spend at least more than a couple of the weeks to solve this one. Even you may not solve this one in the end, okay? But by using the thermodynamic database is considering the Gibbs energy. Inside of Gibbs energy, we have enthalpy, the heat data is already incorporated. So we can do the very simple heat balance calculation like this. We can do the heat balance calculation very quickly. And we spend just about 5 seconds, we can get the answer like this. Okay, then what's the limit of this kind of database? To say frankly, thermodynamic database itself is limit. So we cannot build huge amount of database. And we have in the periodic table, we have the more than 100 elements. And if you consider all the binary combination, ternary combination, and quaternary combination, there's millions of the possible set. So we cannot make thermodynamic database to covering entire of this element. So over the last about even 40 years for FactSage, we can only make a database up to about 10 component system or 20 component system. Even within that 20 component system, we have a lot of holes still actually existing because we don't have time. We don't have actually the people who can actually develop all this database so far, okay? So all this database is developed based on the industrial input. So industry say that, okay, I want to have the database in this area, then we receive the money and we do the project. Okay, so database itself is the most valuable, actually, the product within actually this within this kind in the this CalPad, actually, the society. Then once you have the database, you can do a lot of the interesting calculation, and then you can improve your process. So let's look at the steelmaking plant. Because I'm actually, most of my research is related to the steelmaking process. So steelmaking plant, I would say, is the containing huge amount of different elements within the process. So you know the steelmaking process is as simple as, okay, iron oxide reacting with carbon produce the iron metal, and then there's some impurity, and we have to remove that impurity by using some, you know, fluxes, and we can purify it, and then we can put some additional element to adjust actually chemistry of the steel and then make a product. Yes, that's the everything about steel making, but that element we are considering in the steel is already complex like this. We have iron, manganese, silicon, and all kinds of alloying elements. And we have impurity like carbon, oxygen, sulfur, nitrogen, and hydrogen. And in order to deal with all these kinds of impurity and also deal with impurity from the original ore, we have to consider all these kinds of species here. So if you actually have the good database to reproduce all the problem in steelmaking, I think we can use this database for the most of the other industrial process. So I'm developing the database for this steelmaking process. So luckily, this picture show you actually the group people in our actual lab, and I somehow I'm very popular in our university. So we have about 20 graduate students and 1 research professor. And in order to actually keep this big mass of the people, we need huge funding from the industry. So luckily, I convinced a lot of the steelmaking company around the world and tell them why we have to develop the thermodynamic database and what's the value of this one. And all these 12 companies around the world, they all convinced, and they support me actually my research from 2009. Okay, so we have even 2 Japanese companies, Nippon Steel and the JFE here. Okay, so what we are doing with this actual research project, this research fund, we are developing the thermodynamic database and physical property database, and we try to connect this one with some industrial problem and to make some tools to directly use in the steel industry. That's the major part of our research. And that actually the simulation model we are making is highly connecting to the so-called smart factory. So I'll show you this one later. And this is the overview of our research project in terms of chemistry in the last about 14 years. So we have our core database from our commercial database. And then we expanded this database slowly to the more oxide containing system, more metallic system. Okay. And every 3 years, we have meeting with all the company and decide how we expand the database for the next 3 years. And then for that 3 years, all my students actually take one part by part of this actually database and then expanding it and then increase our database. And by increasing the database, we can find more application in the steel industry and also other than the steel industry too. So one of the examples I want to show you here is the P2O5. So a lot of company was interesting to remove the phosphorus in the steel as much as possible. For example, as low as 10 ppm over the phosphorus. Okay, it's very, very difficult actually the process. And phosphorus is, because phosphorus is very bad impurity in steel. So if you have the higher phosphorus, the steel quality is typically decreasing. And this kind of impurity cannot be actually, this impurity is coming from the iron ore and the coke we are using in the original process. So we cannot get rid of this one easily, okay? So people design the process to remove the phosphorus. So this is the typical phosphorus removal reaction. So we have the phosphorus in the liquid steel, and then if you inject oxygen, we can make a P2O5. If I do this one as a forward reaction, then I can reduce the phosphorus content. So if you're now considering the environment, if we increase the oxygen partial pressure, then we can make a more chemical reaction forward, okay? And then if we decreased this P2O5 in the slag, if we decrease the activity of this one in the slag, so if we make a P2O5 more stable in the slag system, then we can also accelerate this chemical reaction to the forward reaction. So that's actually the system. That's the design of the system. So in this kind of phosphorus removal can be done in the many different stages, but most of the time we're actually using so-called basic oxygen furnace, and this is schematic diagram. So we injecting the oxygen. So oxygen is already, injected here, and then we are adding different kinds of plugs for the slag, which can capture the P2O5 as stable as possible. That's actually slag here. Okay. So in real chemistry, if you look at actually inside of this system, it's very complex. We have gas phase, which have the nitrogen and CO2, because by injecting the oxygen, we also removing the carbon in the liquid steel to make as a CO gas. So we have CO2 is coming from there. And then we have slag, have different kinds of species. CaO, we are adding it by ourselves to make a Ca, and because CaO and the P2O5 like near each other, so it can stabilize the P2O5 very highly in this kind of slag. Okay, and then because of the injecting the oxygen is not only reacting with the carbon or phosphorus, it will react with the iron itself. So it will make a lot of the iron oxide as well. And there's some silicon impurity also can be burned, some manganese can be burned, and also and there's a little bit about aluminum, or sometimes we have the aluminum is coming from the some other impurity. So we have this kind of the chemistry typically for the slag system. So it's already 6 or 7 component system, okay? And then we have liquid steel, also have the many different components. So in order to actually understand the deep complex chemistry, we have to know the thermodynamic property of all these solid, liquid, and the liquid metal and slag and gas phase, okay? So many people already, this kind of phosphorus removal research was already started from 1940, okay? And already in the 1950, many people start to suggest some equation to remove the phosphorus. And this is one of the equation in the 1970. They say that the phosphorus content in the slag and the metal have this kind of relationship by adding the CaO in the system. Okay, this is only containing CaO. And Suito and Inoue, who was in the University of Toku University, and they suggest another equation like this: phosphorus in slag divided by phosphorus in the metal. So phosphorus distribution between the slag and the metal can have this relationship with the different slag components now, CaO, MgO, P2O5, MnO. But you don't see that SiO2, you don't see that Al2O3, you don't see that MnO, you don't see that other species, yeah? So there's no universal equation. So if we have the good thermodynamic database, we can expand this one further. So that's the idea. So we try to make the P2O5 containing thermodynamic database, especially for the oxide system, covering all these kinds of species, okay? And liquid steel, luckily, we already had the database at the time. So for each binary oxide system, CaO, for example, P2O5, we developed the Gibbs, we defined the new Gibbs energy for all the stoichiometric solid phase and liquid phase by using simple equation like this before. And also we defined interaction of the CaO and P2O5 in the slag by using this kind of Gibbs energy. And this is, for example, one of the examples for the P2O5 Gibbs energy itself. So P2O5, this is the single component system, P2O5. We have solid data, and then solid plus gas evaporation data, liquid plus gas evaporation data. So believe it or not, the pure liquid Gibbs energy of P2O5 was not very well known. And so there's several actually the equation available, but all these equations have certain assumption before. And then by using this data, we re-evaluate Gibbs energy of the liquid phase, and that actually Gibbs energy of liquid phase was luckily very close enough to the previously evaluated data based on some assumption. So we believe that our equation is more accurate than the previous one, but luckily this is very close enough. And then once we have the CaO and now P2O5 Gibbs energy, now we can start actually binary system. So we collect all the experimental data, for example, phase diagram data, enthalpy data, entropy data for each solid phase, and then activity data for the liquid phase, and then Gibbs energy data for all the solid phase as well. Okay, and then in the end we can reproduce phase diagram like this, and we can reproduce all the Gibbs energy, enthalpy, activity data over the different phase like this way. So we did a lot of exercises like this. This is FEO P2O5. The data is only available up to about 25% of the P2O5 system, because if it's above this one, you have evaporation of P2O5 from liquid to the gas phase. So you cannot actually do the experiment anymore. So we are based on the limited data here in this area, in the FEO rich side, we have to make a prediction even for the higher P2O5 condition as well. So this is the predicted data. So we did all the binary database development. We combine them together, go to the key ternary system. We cannot have the entire actual combination either because we don't have enough time and enough data. So we did a key ternary system, and then we make a database for the multi-component system and apply this one in the real, for the real process. So for example, for the real process, we have to do the calculation like this. We have molten steel containing phosphorus, we have slag containing P2O5, and we have gas phase containing oxygen. So we want to do this kind of chemical calculation based on the change of the composition in the metal, slag, and the gas phase. So our new database here for the slag is utilized in this calculation. So this is one of the phase diagram we can draw, CaO, FeO, P2O5 ternary system. And there's the phase diagram. It's already a phase diagram experiment was already available, and our calculation can reproduce all those phase diagram data. Along this line here, CaO liquidus line here, they measured phosphorus removal between the slag and the metal. So this is the one of the actual data which come from the Japan. And so there's the phosphorus, and y-axis show you the amount of phosphorus in the metal to the slag in log scale, and x-axis is the amount of the FeO in the slag in this ternary system on the C4P saturation and CaO saturation condition. And all this data with a different temperature in the wide range of composition can be very well predicted. We didn't fit the data. We have slag database and we have metallic database, and we just combine them together to do the calculation, and then we can get the very accurate reproduction of the real process data. And this is the phosphorus content in the liquid metal changing with the slag composition. As you see, it's huge drop in the beginning and then almost flat, and all this trend is very well reproduced by our thermodynamic calculation. So we can say that our thermodynamic database is very applicable. And this is a more complex system. Again, Seito and et al. In the Tohoku University did many experiments in this area. And so, for example, one set of data at this B condition, I'll show you like this. So this is again log distribution of phosphorus in the between metal and slag with the composition of FeO, so increasing in this direction, and at 3 different temperatures. And as you can see, experimental data and the calculated data is quite well matching each other. So, and then we did a huge amount. We collected all the literature data up to about 2010, and we compare them one by one. And within this area, so this is calculated value, this is the measured value. Within this actual data set, we have the more than 1,000 data points. And as you can see, most of them is very well reproduced, and some of them is a little bit off. But this is actually the typical accuracy of the phosphorus distribution data in the literature. So we are very happy because our database can reproduce data very well. And then we try to apply this one in the real process, in the real industrial process. Okay, so this is real industrial process data. So this is the LP phosphorus distribution between slag and the metal in log scale. So this is log LP in the plant data compared to the calculated data. So if it is on this dotted line, it means it's perfectly matching. But as you can see, it's quite well deviated from this perfect matching data set here. Okay, And also one of the things very interesting is our calculation show you that, I mean, for example, this data set here from 3 different plants. So this data set here show that according to our calculation, LP, phosphorus distribution should be about LP log scale equal to 2, it means about 100. So 100 times of phosphorus going to the slag, and only 1 is existing in the metal. But so it should be like almost constant, but according to the plant data, depending on the operation, it's changing from almost 10 to 1 to 100. It changed very wide range. And similarly here, from the one plant, we can have complete different data set. One plant, you have this data set here and this data set here. The chemistry is exactly the same. So this is actually huge problem. So we have good thermodynamic database. We believe that our database can reproduce laboratory data, but this database cannot reproduce plant data. Why? Because plant is not in the equilibrium state, because it's a dynamic state. So we have to consider kinetics in the plant. Otherwise, we cannot explain this kind of the deviation of data. Okay. So then you can have question. Okay, then what's the value of thermodynamic database? I mean, thermodynamic database is already, very good, because thermodynamic database can tell you at least where we are heading for, because thermodynamics tell you what's the final equilibrium state. And all this data is moving to the final equilibrium state, but because of the kinetic problem, it's not reached to the final equilibrium state. So from this point, we were thinking, okay, is there any way we can combining our thermodynamic database with the kinetic to predict real plant operation? Okay, that was about 10 years ago. So we tried to actually put up some idea, and then that is actually the baseline of the so-called the digital twin smart factory project. Okay, so now let's move on to the new subject. So we are talking about basic thermodynamic equation, basic chemical reaction. I show you CalPAD database. We have good thermodynamic database, and we want to now go to the plant. Okay, and one of the hot issue in this day in the steel plant is so-called Industry 4.0 or smart factory. So the basic idea about this Industry 4.0 is, in the plant, we have a huge amount of the operation data. So we have big data, okay? And by using so-called artificial intelligence, you can analyze all this data, and we can make a black box model. But that black box model can be useful for the process optimization, for the current process. So we want to actually control the system within the current operation as good as possible, as efficient as possible, as economic as possible by using this big data analysis using the AI. Okay, that's the Industry 4.0. So in the laboratory, in the university, we cannot do this big data analysis, unfortunately, because we don't have a data set. Okay. And however, we can see that already there's critical weakness of the big data actually approach in the plant. So for example, let's look at this one. So x-axis here is the process parameter, okay? Y-axis is certain target property, for example, in the operation. In the current operation condition, we have huge amount of data set, okay? So we can find a very good correlation of this one, even by using the Excel, pitting or AI pitting, okay? So we can do we can find very good solution for within this area. But let's assume we want to go to the new process area, new area here, and which we never actually try a lot of operation so far. So, and also, let's assume there's only one data point, one plant data point here. Depending on whether this data is noise or real data, we can have completely different prediction. So for example, we can have prediction like this, assuming that this is noise data, or we can have prediction like this, assuming that this is good data. This is huge gap. And in steel making, we are talking about 300 tons of the steel is moving around every 1 hour, okay? And if you make a mistake, you actually discharge entire 300 tons of the steel. It's a huge amount of money. So nobody, no engineer can actually say that this is noise or real data and then very bravely make operation like this or operation like this. So nobody wants to take responsibility, okay? So we want to make something which is useful not only for the current operation, we want to make something predictive for the future operation condition. That's what we want to develop in our research group now, okay? So big data analysis based on the plant data is very good for the interpolation. Within that actual data set, it's very good. However, extrapolation is very bad because you don't know how to treat this data, okay? But this kind of the change, if there's change of shape like this is coming from the chemistry or physics of the materials. So thermodynamics actually containing those kinds of the physics and chemistry, okay? So by using this kind of thermodynamic with a certain kinetic, we can probably make a predictive model. That's actually our idea. So this show you actually the very simple diagram, because my kid always asks me, okay, Papa, what are you doing? What's your research? And my kid especially like a tank like this. So I try to explain my kid what I am doing, okay? So here, this is current data set. Based on your big data analysis with AI or thermodynamics, we can fit this data. Okay, we can exactly aim this one and then shooting our, the missile and then hit it here. But now, if you have the new data, new area, if you change the now angle, now the final actually the position for your missile actually attacking could be completely different. So if you have the good model, you can actually target by one shot, okay? And this is the value for the thermodynamic model. So this is the one example. So here, this is the oxygen content in the liquid steel with the addition of the aluminum in the liquid steel. So for example, let's assume oxygen, about this is in log scale, by the way. This is about the 100 ppm of oxygen in the steel. And by addition of the aluminum up to about 1000 ppm, we can reduce the oxygen content from 100 ppm to almost 2 or 3 ppm, okay? Can you tell this is continuously going down or going up? I mean, luckily in this case, we have data and we show that there's a minimum and then going up again, okay? But if you are AI, you cannot tell how to move because our operation, current operation in this area, and most of our future operation, especially to make a light steel alloy, we have to add more aluminum, then it goes to this area. And so if you don't do the operation here, if you don't have this operation data in the plant, we cannot predict. And this is the same example I showed you before, this phosphorus distribution between slag and the metal. So for example, here we have maximum. So if you are doing plant operation only in this area, you can make extrapolation like this, and which is completely wrong according to the experimental data. But thermodynamic model can give you the good answer already. And this is also prediction. So we know this one, prediction of the thermodynamic calculation, and we can make a prediction like this for the multi-component system without any additional parameter. So we can make a prediction of the certain system. And this is another prediction case. So here, this is the very high alloy composition, iron, manganese 24%, silicon, carbon. And we want to know what's the nitrogen content depending on the aluminum addition in this liquid metal at 3 different temperatures. Before we have these 3 data points, we did a prediction first. And then we got the data point from our colleague. And we say that, okay, our prediction was very, very accurate. Okay, so our database, thermodynamic database, is now good enough for the predicting to the new area. That's what I want to say. And this is another example. And this is the solidification of very complex plugs here, which is used for the steel making for the casting process. And we make a prediction like this. And this data point was obtained from the Tata Steel in Europe, because Tata Steel in Europe, they didn't believe our prediction. So they did their own experiment and then proved that our calculation is very accurate already here. So it's very nice. So we have good thermodynamic database for the wide range of composition, wide range of operation condition. And if we can connect this database with kinetics, then we can make process simulation model. And of course, this kinetic is depending on the plant by plant, okay? So we have to tune a little bit of that actual data based on the plant data. Then we can make a very good predictive model. So that's our process simulation model idea, okay? So if you're actually considering the kinetics, one of the simplification we can think about in solid state is solid state diffusion equation, the fixed first law and second law equation, for example. So diffusion of species in solid state is depending on the diffusivity and times with the dc of dx, yeah. So this is very well applicable in the solid state. But however, in the liquid state, it's a little bit more complex. For example, in the solid state, even you actually shake your solid, the atomic diffusion inside of solid is not changing because its atom is really moving by itself, or vacancy is moving by itself. But if you have liquid phase, so for example, if you have the coffee with milk, if you're stirring actually the milk and coffee with your straw very high, then it can mix much quickly. And so in the liquid state, the diffusion is not just diffusion by the atom itself, by the stirring energy, by increasing actually stirring, you can accelerate of the mixing. So in case of liquid state, we don't express diffusion in this way. We express flux as a so-called mass transfer coefficient times concentration difference like this, okay? So for example, when you have liquid metal and liquid slag is reacting together, we have to consider chemical equilibrium at the interface here. And then depending on the concentration profile, we can move the atom from liquid to the slag or slag to the liquid. So for example, let's look at this example here. So when A in the metal is high, then actually the A in the interface at the equilibrium state, then A metal want to actually move to this direction naturally. And then A oxide can also go in this direction. So this slope here is more or less equilibrium constant, Km, okay? And this boundary here, dotted line is the so-called the diffusion boundary in the liquid actually the process. And this diffusion boundary can be changed depending on your stirring energy in the metal. So if I stir more, this becomes smaller actually boundary between this liquid metal boundary to the actually this mixing boundaries become smaller. So this become more steeper. So Km become bigger, okay? So K, mass transfer coefficient, is changing depending on your fluid dynamics a lot. And this should be considered in the liquid phase kinetics, okay? So, and then also now how to connect then kinetic, this kind of kinetic process with the thermodynamic. So look at this one. So let's assume we have liquid gas phase here, and we have liquid phase here, we have solid phase here, we have three-phase equilibrium here. If you leave this one forever, entire gas phase, entire liquid phase, entire solid phase will become equilibrium state, okay? But if you actually look at the very short time frame, certain part of the gas and certain part of liquid will react together and then make equilibrium, local equilibrium. And similarly, we have certain solid phase, liquid phase reacting together as a local equilibrium at the given time. And then if this actually take a longer and longer time, then we can have full equilibrium for entire area, okay? So if we can dictate how much is this local equilibrium for each time, and then if we can dictate how much of those local equilibrium can be changed depending on the stirring energy in the system, then we can do the local equilibrium calculation by using the thermodynamic database we have. And then we can connect them with the time. We can do this one iteratively. Then we can actually show how does the composition can be changed with the time for the entire system. That's the idea of our process simulation. So local equilibrium concept is basically the kinetic process, the key for the kinetic process. And then while we are doing that, also we can do the heat balance calculation simultaneously, because that's just what thermodynamics is doing anyway, okay? So we can track composition plus heat or temperature. So this is show you actually the schematic diagram of our concept. We call this one as effective equilibrium reaction zone model. So it's basically local equilibrium actual model. So we have liquid metal here, we have slag. At the given time, certain part of this liquid reacting with a certain part of the slag at the interface. And then once it is reacting, then this the reacted actually the metal can also homogenize with the rest of the metal, and this reacted slag can homogenize with unreacted slag. And then in the next time frame, we have another chemical reaction happen here, and then homogenization. If you do this one iteratively, we can trace chemical composition change of metal and slag with the time. Okay. Then how can we define the local equilibrium amount at the interface? That's determined from the mass transfer coefficient directly. So the amount of the metal which is reacting at this interface at the given time is given time times mass transfer coefficient in the metal times density and the area of this chemical reaction area here at the interface. So by knowing this mass transfer coefficient, we can find out how much metal is reacting at the interface. And this mass transfer coefficient is, as I told you, is the function of the mixing energy, the stirring energy in the metal. Okay, so we can define, if I know this one with the changing with the time, I can calculate how much metal I need to calculate with the time. Okay, and by combining this with the thermodynamic, we can now make process simulation model. So I'll show you two examples. So one of the first one is the ladle furnace simulation model. So ladle furnace looks like this schematically. So we have about 300 tons of the liquid steel here, and we have a lot of the impurity like oxygen and some inclusion inside. And we want to control this kind of impurity by adding some new element here from the outside. And for example, we can add aluminum and silicon to remove the oxygen to make alumina, and then that alumina going to the slag. And also we want to remove some sulfur, and that sulfur can react with the slag to make a sulfide actual component in slag. And then in that way, we can purify the steel. And also we can add a lot of the new metal inside to control the final chemistry of the steel. By doing that, we can decrease temperature of the steel. So we are using arcing to maintain the temperature for the process. Okay, so it's very complex. So it's a 300 tons of steel is actually working within about 40 minutes. Okay, so it's not going to the final equilibrium state. So if you actually look at the inside of that system, we can divide all the interaction area at all the interface area like this. We have, for example, slag metal interface area here. So we have to consider that kind of chemical reaction. And while also we have to consider the heat balance reaction at that time. And if you are doing arcing, we have heating of the arc to the slag and also metal. And we have new alloys coming in, then we have to consider dissolution. And if you're adding some aluminum, for example, aluminum can react with the steel. Aluminum can react with also the slag simultaneously. And then we are losing certain amount of heat to the atmosphere. And if you're adding some new flux to the slag, that actually have dissolution inside of slag and etc. So it's a very, very, very complex. And also this stirring energy is controlled by the argon bubbling or nitrogen bubbling from the bottom. By injecting different amount of the gas phase here, we can control the stirring, actually the speed, okay, stirring energy, okay. So it's a very complex system. So what we are doing, we put by using the plant data, we try to find out the mass transfer coefficient equation depending on their operation condition. So that's the only thing we are pitting, and because this is key component for the slag metal reaction, okay. After that, we just did everything as a prediction from the thermodynamic calculation. Okay, so this is the input we typically provide for our company. So this is the amount of steel and the chemistry. So you have initial amount, in this case, 165 ton, initial temperature 1600 degrees Celsius. This is initial steel chemistry. So we are not doing pure iron. We have aluminum, carbon, calcium, chromium, copper, manganese, all the impurity elements. Okay, and this is initial slag, about 5 tons of slag at this temperature with a different chemistry here too. And then we are adding different kinds of slag, flux. In this case, we are adding only one. It's not pure CaO, it's a CaO with all the impurity. And we are adding different kinds of the metallic species, up to about 9 different kinds of metallic species during the operation. So we provide all those possibilities, with including all the impurity, because this minor element is very important for the final inclusion composition inside of the steel, which is very bad for the steel, okay? And then we consider initial temperature and the melting rate and temperature of the initial steel and slag to predict temperature profile of the system. And this is operation condition. Every 1 minute, they inject a different amount of the gas from plug 1, plug 2, and then they have electrical energy heating at certain point, and then this is the heat loss through the wall and also atmosphere. And this is the scheduling to adding different kinds of species during the operation. So you enter all this one, and then you just learn the calculation mode, then it just do the simulation by itself. And all this line here showing you the simulation result, and all the data point is the plant sampling data. And again, Tata Steel was very curious about the accuracy of our model. So they did the sampling every 2 minutes in the plant. And typically they do only 2 sampling in the operation. But for this to validate our model, they did every 2 minutes sampling. So it's a huge amount of data was collected. To analyze all this data, it took 6 months even. And then in the end, it's beautifully fitting with our data, our prediction. The temperature, very well fitting. And then the slag chemistry change, very well fitting. Even metallic composition change, very well reproduced. Even inclusion inside of steel was very well reproduced. And now what Tata is doing, they are learning our simulation for virtual simulation. And then they try to make a big data now, and then making their own model based on that. And this is another impurity they are actually very looking for. So this is the sulfur content in the steel. So this is the measured sulfur content and calculated the sulfur content from our model. It fit within 10 ppm range. So this is very accurate model. And similarly, we also make many actually different simulation. And this is the BOF process model. So this is basic oxygen furnace I showed you before. And in this operation, we have about 250 ton of liquid steel with about 50 ton of scrap solid adding in the beginning. And then we are injecting the certain amount of the flux like a CaO. And then we inject the gas phase, oxygen. And this oxygen is very, very high speed oxygen. So because of impact energy, oxygen to hit actually this steel. And there's a lot of liquid droplet can be formed. And this liquid droplet is traveling inside of slag and then make chemical reaction. It's a very, very dynamic process. By using this dynamic process, we can remove the carbon from 5% to the 500 ppm within 18 minutes. So it's a very, very violent, very dynamic process. It's almost impossible to do any sampling of the data inside. Okay, so this is kind of black box, kind of the process so far. So we actually we make actually our model based on all the literature, idea, and then by using this simple actually connection between thermodynamic and kinetic, we can reproduce all this plant data very well. So this is one of the plant data available. So this is from Argentina, and then they changed actually. So this is operation condition, and then over the time they make a sampling of the composition like this, and this is the change of the carbon content, and change of the manganese content, and change of the phosphorus content in red, and change of silicon content, and etc. And all this data was very well reproduced by using our simulation. And this is the outlet gas composition, also very well consistent with their plant operation data. And this is change of the slag composition, and this is schematic diagram of the chemistry change in slag, and our data show you actually very well consistency. And this is the change of the mass in the slag in the inside of that furnace. And this is total amount of slag. This is the liquid amount of slag. This is solid amount of slag. And this is very well consistent with the known knowledge of this plant. And this is change of the temperature. So, once you have this kind of simulation model, as I told you, we don't want to use this one only for the current process. We want to utilize this one for the future process, okay? So this is one of the example, and because one of our sponsor company was POSCO, and POSCO have a chance to buy the new ore from the China, for example, which containing very high amount of phosphorus as impurity in the ore, okay? And they used, because unfortunately, they cannot do the test of this kind of iron ore, because they have to start from the blast furnace, and then do the old operation. And then if it's not working very well, you can actually stop the entire plant. So you cannot do the plant, study like this for the new ore. So what we did is we did a simulation for that new ore composition, whether by using that new ore, we can still do we can actually produce a good quality of steel or not. So we manipulate all kinds of the actual operation condition, and then we show that it's almost impossible to produce good actually the steel in the end of the process within the economic actually the process range. And this is one of those simulation results. So we say that, okay, depending on the change of the phosphorus content, okay, if you are doing certain variable like this, the phosphorus actually distribution between slag and the metal is changing in this direction. And then we say that this is not good enough or good enough for their process. So for example, when you have the low phosphorus content, you can have this one. Okay. And if you, I'm sorry, low phosphorus content is this one, sorry. And if you have a low phosphorus, sorry, it's a higher one. So you can have very good removal rate, because this is high means you can have very good removal rate. If you actually go to the 0.5%, you can have very low removal rate. So it's almost 50 times difference. Okay. So we cannot remove the phosphorus very well if you're actually using the high phosphorus containing ore. Okay. So based on this simulation, actually, they make a decision to not actually to purchase that ore. Okay, so this is the value of the simulation tool like this. So we make a simulation tool for the entire secondary steelmaking refining process, and over the last about 6 years, and we are making actually now next stage operation tool, which can go to their dynamic in the plant model. Okay. So many people already see that this is very useful. So we did, even within our consortium meeting in every year, we do the consortium meeting. Within our consortium meeting, we do the so-called smart factory session. And then we have like a presentation by the different company and showing that what is the activity they are doing for the smart factory actually process in their plant. And then this is one of the slide I steal from the Tata Steel, presented about 2 years ago. They say that this is the 10 different kinds of things they have to establish in their plant for the smart factory, okay? And one of that year is the simulation and digital twin. So this is the twin factory, which can be almost one-to-one for their real plant. And inside of this twin factory, they say that TechSage is the key point. Our simulation tool is the key point to develop their actually simulation model. And this is another slide from Hyundai Steel. So this part here is our simulation tool. And they want to actually using our simulation tool, by doing calculation of this one, they want to make their own guidance model. And by using this one, they want to do the operation, okay? So the simulation tool is one of the key components for the smart factory project for the Hyundai Steel as well. And many other companies, same thing. Okay, so, and we are moving now next level. So we have all this process simulation tool. What we want to do is now, we want to go to the next generation smart factory, okay? So current smart factory in the post-industrial revolution, digital twin, they are based on the big data from the plant. And in this big data, there's a lot of noise. So first of all, you have to remove all the noise to get the good data set. And then you have to use the AI to make a smart factory. But the advantage of this one is very good for the optimization of the current operation. As I show you, disadvantage is extrapolation is very bad because they are based on only within the limit of their current process data. So sometimes if you're just outside of this one, your extrapolation is completely wrong. So it's very bad for the future actually production. In our model, however, we are very good. We are actually based on the chemistry and the physics. Okay, so we believe that our data, the interpolation and extrapolation, both of them is very good. And by using this actually model, we want to make a big data, which have almost no noise. And then we want to provide this one to the AI to establish next generation smart factory. So this is what we are actually doing in the next 3 years. And then we want to demonstrate that this is really working in steel plant. And one of the actual company already start to collaborate with this or with us for this actual project. Okay, so this is my last slide. So I say thermodynamics is very, very important. A lot of people feel that thermodynamics is very difficult actually knowledge, but as I show you, the thermodynamics is very simple. You don't have to remember first law, second law, third law of thermodynamics. You have to just get the sense about the Gibbs energy, especially in order to change your system. Depending on the system, your activity of species can be changed. So you have to understand this interaction of species within your solid, liquid, and gas solution. That's actually the thermodynamic part, okay? And then if you connect that with a simple, even kinetic actually approach, and then connecting with the industrial experience, you can make a very nice predictive tool, which can be applicable not only in your the laboratory experiment, but for the industrial scale as well. And this kind of the tool is very, very useful to make a new product and save a lot of money for the current process as well. So thermodynamic, I would say, I hope you enjoy the thermodynamic. You don't have to actually, you should not get rid of thermodynamic, unfortunately. I hope you can actually see that what's the value inside of thermodynamic. And then I want to actually finish, and with that, I want to finish my lecture today. Thank you very much for everybody to listening about 1.5 hours of my talk. Thank you.
Professor Chen, thank you so much. I think you have some time to accept some questions.
Yes, for sure. Yeah.
Students, any questions? Taking this opportunity. Tomoya-san, you can turn on microphone and make question.
Yes. Yes. Thanks for your presentation. I'm very glad this your precious speech. And I have one question. And in page 45 slide.
Okay, just a second. Go back to the 45. Okay. Yes.
Yes. I can't understand how to predict this entire phase diagram from limited data.
That's actually a very good question. I say I predict. I'm not sure whether it's very accurate. But the way I predict is we analyze all the binary P2O5 systems. So for example, CaO P2O5, MgO P2O5, FeO P2O5, MnO P2O5, and etc. And then we can find the kind of trend of the Gibbs energy for the solid compound, depending on the M oxide system. And also we can find the trend even in the liquid Gibbs energy as well. So based on that kind of the trend, we make a prediction.
Thanks.
Thank you very much.
Thanks for your answer.
Any other question?
May I ask you a question?
Sure.
Thank you for your lecture. Maybe to describe all reactions in steelmaking process is great and great method to build the smart steelmaking process. So why the ancestors did not come up with such building equations?
I don't exactly understand your actual last part of the question. So can you repeat again? So you say why previous people cannot did it or didn't do it?
Yes. So why the Yes.
So a lot of people actually try to do the process simulation, okay? And but most of people, when they actually did this kind of process simulation, they didn't have the thermodynamic database, very good thermodynamic database. So they did a very simple process simulation, like considering the only sulfur removal, for example, or phosphorus removal, or carbon removal. But they could not do all this one simultaneously because they don't have the good thermodynamic database. Okay. So I mean, the process simulation was a very long history. I mean, had very long history. A lot of people tried that, but unfortunately, most of people didn't have the good thermodynamic database, so they could not have the actually, this very complex simulation before. But luckily, in our case, we are making our own database, so we could more easily actually apply our database in this simulation. Yeah.
So FactSage can provide you with a good thermodynamic database.
Yep.
Thank you.
Any other questions? Questions?
I hope you enjoy the
Tokyo or
thermodynamics is very good, yeah. You can do a lot of things with the thermodynamics.
questions from Tokyo or questions from Korea? Questions from Seoul?
Any question? Question from Professor Morita. Morita is not here. I'm sorry.
I'm sorry, he is already leaving.
Yeah.
So.
Yeah. Okay.
Can I ask you a more question?
One more question.
Yeah, sure. Yeah.
So you set the EERGM,
Yep.
effective effect, the zone.
Yep.
In EERGM, the is mass transfer coefficient constant or a determined value.
Yeah.
I wanted to check the fact that Ki of all species are same value. So.
Yeah, it's a very good question again. So I mean, so typically this Ki, mass transfer coefficient, is different depending on the element. Okay.
Yes.
However, however, if you look at the real value, the order is almost same. Okay.
Yes.
And also the other thing I have to really say that is because so if you are doing the very static, almost no stirring condition. If you have very static condition,
okay,
of course, the diffusion, intrinsic diffusion of element inside of the metal determine the mass transfer coefficient. It's by element, okay? But now if you have the very strong stirring condition like this in the industry process, because stirring energy determine most of the actual mass transfer. So even you have the sulfur element here or carbon element here, if you actually stirring it, the stirring energy can drive this one going to the interface. Okay, so mass transfer is mainly determined by the stirring energy. So even you have different element have different, the kind of mass transfer coefficient, they are not that much different in reality if you have the very strong stirring energy. In case of the slag,
sorry, what is stirring energy?
Stirring energy, yes, stirring energy. So if you actually inject the nitrogen or argon gas, if you mixing energy, yeah, basically. Yeah.
Yes.
And in case of slag, it's a little bit different. It may be changed depending on the species, because slag is very viscous material. So even you do the stirring, the element inside is not moving very quickly. And however, within our simulation we have done so far, we proved that by using almost constant, the same mass transfer coefficient for all the species, it works reasonably well. So that's why we're using only one overall mass transfer coefficient in our simulation, because otherwise the model is over complex than actually the available data. So we try to make it more simpler actually approach for the mass transfer coefficient data in this case.
Thank you so much.
Any other questions?
Like Korea, Japanese student is also very shy.
Yeah. How about students in Seoul? Any questions? No questions? I think they can ask anytime. ね。よろしいですか? So, Professor Jan, what about assignment for students?
Oh yeah, I have to prepare it. I'll send you tonight.
So, do you need to explain something?
So I want to give the subject like I mean the one of the big actually the issue in steel industry in this day is the carbon neutral.
Okay.
Carbon neutral. So
Carbon
I want
neutral.
to actually student to make a report about what kind of action is going on in the different steel company to achieve the carbon neutral for the steel industry. That's actually the assignment.
Big issue. Okay, sounds very good. So I'm expecting you will send me in a few days.
Yep, I'll do that. Yeah.
So after that, I will share with the students the assignment and report subject.
Okay.
Hi. If you have no more questions, then this is the end of today's special lecture. Okay. So students, let us express our special thanks for Professor Info-Jan again.
Thank you very much. Thank you very much.
Thank you so much.
Thank you very much. I hope you enjoy my lecture. Thank you.